Hello, I'm Hao Qingxu from Southeast University. I'm going to introduce our paper, Adaptive Group Personalization for Federated Mutual Transfer Learning. This is a joint work with Dian Shen, Meng Wang, and my advisor Beilun Wang. Mutual transfer learning was proposed to efficiently solve the big data learning tasks with multiple data domains. It assumes that each data domain is able to be a source or a target domain. Similar domains would therefore form clusters. We call such clusters as the learnability structure in mutual transfer learning. The learnability structure is often recovered from raw data and can improve the model learning. It is a key to understand the data since it can reveal the inherent relationship between domains. For example, in climate analysis, it will be represented by climate zones. In recommender systems, it's user preferences, and so on. However, when dealing with large-scale data, centralized mutual transfer learning faces the challenge of communication overload. Clients may collect TBs of data and transfer all of them to the server, which is expensive and time-consuming. Meanwhile, in some applications like healthcare analysis, raw data may contain private information about users. Upload them to a third-party server may cause ethic issues. Nowadays, federated learning provides a sound paradigm to resolve the two challenges. In this paper, we focus on the federated mutual transfer learning that only transfer parameters instead of raw data. However, there exist two challenges in applying federated learning to mutual transfer learning. The first one is learnability heterogeneity. In the common linear model, parameters are shared among all the domains, while in mutual transfer learning, global and heterogeneous parameters have different transferability, which is formalized by a linear mixed effects model as shown on screen. Previous single-model federated learning methods are not able to recover the learnability structure or benefit from them. There is also no simple way to distribute previous centralized mutual transfer learning methods to the clients. As a result, our first goal is to realize federated learnability structure recovery and estimation. The second challenge is the concept-driven problem. With federated learning framework, the learning may last for a long period of time. Data distribution, such as user preferences, climate zones, may change among different time steps. However, previous mutual transfer learning methods can only consider the stable data distribution. For example, DFS applies a fixed threshold on the standardized domain difference to distinguish the domains from the same subcluster. While the data distribution changes, a fixed threshold may lead to false positives and the learnability structure would be wrongly recovered. To overcome this challenge, we propose to adaptively correct the clustering threshold based on the current data distribution. We found that the optimal threshold can be observed by comparing the density of standard domain difference and the chi-squared distribution. With the optimal threshold obtained, we can further cluster domains via the learnability structure recovery function proposed by DFS. For challenge 1, we designed a group personalization framework for mutual transfer learning under federated settings. We aggregate the parameters either globally or group-wise, depending on its global or heterogeneous, based on the recovered learnability structure. To summarize, we propose the adaptive group personalization for federated mutual transfer learning, ADAGroup for short. ADAGroup can provide accurate, robust, and tuning-free learnability structure estimation and parameter estimation under the federated framework. The overview of our method is shown on the screen. Firstly, ADAGroup performs local update steps on clients with data and type set tau. The local steps are sent to the server after updates. The server computes the standardized domain difference and uses the non-parametric k-nearest neighbors to estimate its empirical density. A DAG group uses the adaptive threshold correction function mentioned before to obtain the optimal threshold lambda star. We use the corrected threshold for domain clustering and obtain the learnability structure. The parameters are aggregated in a group personalized way and then sent to clients for the next round of updates. After our communication rounds, the parameters and the learnability structure converge and they become the multi-structured learning estimation at time step tau. We theoretically prove that a DAG group is able to perfectly recover the clusters, and show that a DAG group relaxes the condition compared to the previous method. A DAG group can cover more cases of data, while baseline DFS can only work with certain data distributions. Results in synthetic data indicate that a DAG group achieves the best and the most stable performance compared with baselines. In the real-world climate analysis task, a DAG group provides the most proper estimation similar with the IECC climate zones, illustrating it is competent in real-world applications and easy to apply. For more details, please refer to our poster and the paper. Thank you for your attention.